Master challenging mole concepts and complex stoichiometry problems in chemistry. The mole is chemistry's fundamental counting unit, representing 6.022 times 10 to the 23 particles. Let's explore limiting reactants, which determine how much product can form. The limiting reactant is the reactant that gets completely used up first, stopping the entire reaction. Consider this reaction. 2 molecules of hydrogen plus 1 molecule of oxygen produces 2 molecules of water. If we have 5 molecules of H2 and 3 molecules of O2, which one runs out first? According to the ratio, 3 O2 molecules would need 6 H2 molecules to completely react. Since we only have 5 H2 molecules, hydrogen is our limiting reactant and will run out first. Now let's solve a challenging multi-step stoichiometry problem. We'll calculate the mass of product formed when given masses of 2 reactants. Consider this reaction. 4 ammonia plus 5 oxygen produces 4 nitrogen monoxide plus 6 water. We're given 25 grams of ammonia and 40 grams of oxygen. We need to find the mass of nitrogen monoxide produced. First, we convert the mass of each reactant to moles using their molar masses. The molar mass of ammonia is 17 grams per mole. So we have 25 divided by 17, which equals 1.47 moles of ammonia. The molar mass of oxygen gas is 32 grams per mole. We have 40 divided by 32, which equals 1.25 moles of oxygen. Next, we determine which reactant is limiting by comparing mole ratios. From the balanced equation, the ratio is 4 moles ammonia to 5 moles oxygen. For 1.47 moles of ammonia, we would need 1.84 moles of oxygen to completely react. Since we only have 1.25 moles of oxygen, oxygen is our limiting reactant. Oxygen is the limiting reactant, while ammonia is in excess. Now we calculate how many moles of product form from the limiting reactant. From the equation, 5 moles of oxygen produces 4 moles of nitrogen monoxide. So 1.25 moles of oxygen produces 1.25 times 4 over 5, which equals 1.00 mole of NO. Finally, we convert moles of product back to grams. The molar mass of nitrogen monoxide is 30 grams per mole. Therefore, the mass of NO produced is 1.00 times 30, which equals 30.0 grams. In real experiments, we rarely get the theoretical amount of product. Theoretical yield is the maximum amount of product we could get under perfect conditions. Actual yield is what we actually obtain when we perform the experiment in the lab. Percent yield equals actual yield divided by theoretical yield times 100%. For example, if our theoretical yield is 30 grams, but we only obtain 24.5 grams, the percent yield would be 24.5 divided by 30 times 100, which equals 81.7%. This visual shows the actual yield as 81.7% of the theoretical maximum. Let's tackle empirical and molecular formula calculations from combustion data. The empirical formula shows the simplest whole number ratio of atoms in a compound. The molecular formula shows the actual number of each type of atom in one molecule. Let's solve a problem where a compound is 40% carbon, 6.7% hydrogen, and 53.3% oxygen by mass. First, assume we have 100 grams of the compound, so percentages become grams. This gives us 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen. Next, convert each mass to moles using molar masses. Carbon. 40 divided by 12 equals 3.33 moles. Hydrogen. 6.7 divided by 1 equals 6.7 moles. Oxygen. 53.3 divided by 16 equals 3.33 moles. Divide all mole values by the smallest to get the simplest ratio. Carbon. 3.33 divided by 3.33 equals 1. Hydrogen. 6.7 divided by 3.33 equals 2. Oxygen. 3.33 divided by 3.33 equals 1. Therefore, the empirical formula is C₆H₂O. If the actual molar mass is 180 grams per mole, we can find the molecular formula. The empirical formula mass is 12 plus 2 plus 16, which equals 30 grams per mole. The multiplier N equals 180 divided by 30, which is 6. So the molecular formula is C₆H₁₂O₆, which is glucose. Let's review the key concepts for advanced mole calculations. Remember that limiting reactants determine the maximum amount of product that can form. Always convert to moles as the bridge between mass and chemical equations. Percent yield helps us understand the efficiency of our chemical reactions. Empirical formulas can be converted to molecular formulas when we know the molar mass.